Hello everyone, and welcome to the 9th Carbon webinar. My name is Nigel Marks, and on behalf of the Australian Carbon Society and Curtin University, we're delighted to be online once again with our carbon colleagues around the world. For those in the Americas, good morning. For colleagues in Europe and elsewhere, good afternoon. And for those of us here in Australia and Asia, good evening. So before we begin, I'd like to remind everyone that this session is recorded and will be available on YouTube afterwards. And as always, links to YouTube will be available on the #Carbon webinar website. After the presentation, there will be an opportunity for our usual question and answer session. So to ask a question, please type it in the Zoom chat box indicated by the graphic on the screen. Feel free to type your questions into the chat box during the webinar, and after the presentation, I will read out the submitted questions and our speaker will have a chance to respond. Now, once the formalities of the webinar are concluded, I commend you to stay around a little bit longer for an informal video chat using an online platform called GatherTown. A number of you have used this before, and I think it's a very nice way to have a less structured talk once the webinar is over. So with that out of the way, it's time for me to introduce our speaker. So I'm delighted to introduce today Dr. Ryan Paul from Oak Ridge National Laboratory. Ryan received his PhD from Ohio State University, and prior to joining Oak Ridge, spent nearly 10 years working in industry, serving as Associate Director of R&D at Graphite International in Cleveland, Ohio. At Graphite, he led the commercialization of several new products and processes employing advanced material science and modeling/simulation tools. He's co-inventor on 2 patent applications and is expert in carbon and composite materials. In recognition of his achievements in carbon material science, the American Carbon Society selected Dr. Paul as the prestigious Graffin Lecturer for 2021. Before we begin, just a few words about the context of the Graffin Lecture. The American Carbon Society, supported by grants from Ashbury Graphite Mills, sponsors an annual lecture series at North American universities in honor of George D. Graffin, a pioneer in the national graphite industry. Each year, the Society selects a lecturer who has made distinguished contributions to carbon science and engineering. And in 2021, the recipient was Dr. Paul. Now, in normal years, he would have been traveling all over North America, giving this lecture, but due to travel restrictions, he has so far given his Graffin lecture talk just the once. And so here we are online, is the second time this has been presented, so we're very privileged. So the title of his talk today is 125 years of synthetic graphite. I'm looking forward to it very much. Ryan, can you please now share your screen and commence your presentation?
Yes, I will. Thank you, Nigel. So thank you so much for the introduction. Really glad to be here today to speak to you all virtually through this carbon webinar series. Somewhat of an introduction has already been given, but my name is Ryan Paul, and I am giving a series of talks through the American Carbon Society George D. Graffin Lectureship. The title of my talk is 125 Years of Synthetic Graphite, and I hope to make that clear as to why I chose that and why I think that is important as we move forward. So a little bit about the Graffin Lectureship. For those of you who are not familiar, I really encourage you to check out the American Carbon Society website at americancarbonsociety.org. There's also some information on YouTube and LinkedIn around the American Carbon Society. The American Carbon Society was founded in 1957, so we'll be celebrating an 65th anniversary coming up here very soon. But the Graffin Lectureship specifically was initiated in 1978. By the American Carbon Society and supported by Asbury Graphite Mills. And this honors the late George D. Graffin, who passed away in 1977. He was a respected and very recognized authority in the natural graphite, and I think just in general, the graphite industry. And each year, the Society selects a lecturer who has made contributions to the field of carbon and graphite science. And really the goal is to promote interest, promote the word about carbon and graphite. And I join a long list of very respected colleagues going back to 1978 who have given this talk mostly in person, but of course in these days we do a lot virtually, and certainly with COVID, we are doing almost everything virtually for now. But with the colleagues that I knew from my time at Graftech and Oak Ridge National Laboratory, there's a number of distinguished colleagues who have given this talk. And I also encourage you to check out the website for some videos from Julian Norley from his time as giving this talk, and also very recently, Mauricio Terrones. He has a nice video online as well. So please check that out and become more familiar with the American Carbon Society and certainly the past Graffin lectures, not just what I'm talking about today. So a little bit about me. I identify now as a carbon material scientist, although I feel that I've taken a very non-traditional route to get to that point. Actually, my bachelor's and first master's degrees are in the field of mechanical engineering, and I started off studying at Youngstown State University in Youngstown, Ohio. I started off, as I said, mechanical engineering, but during my late undergraduate days, started to do you could say an internship with a local company in the area who they were doing ceramic metal composites. And this actually became the topic of my master's degree working for them. And so at this time, I realized my interests were not so much in mechanical engineering, mechanical design, heat transfer, fluid flow, structural, and dynamics, but I was interested more in materials and how they were made, how they were used. And so that led me to pursue another master's and then a PhD at The Ohio State University. The commonality between the two universities are that they both have very intimidating mascots. The penguin and the buckeye are among some of the fiercest mascots that you can think of. But what actually got me into the field of carbon then, so at the time I was starting my work at The Ohio State University, I was not really yet in carbon and graphite, you could say, but the work that brought me to Ohio State was work looking at graphite as a rocket nozzle material. And this was my first introduction into what manufactured graphite is, what it's used for, and in this particular case, the use as a graphite rocket nozzle, which goes back many decades. From once that work wrapped up, the funding from that was being wrapped up in about 2009, and so I pivoted from that point into what at the time was a very hot topic and still is very interesting. Not as much fundamental research being funded exactly today, but in the field of oxidation of nuclear graphite for nuclear reactors. And so that was the topic of my PhD work, was studying the oxidation, the air oxidation of nuclear grade graphite, and how the graphite could degrade in an accident scenario that could occur for nuclear reactors, gas-cooled nuclear reactors. So after I graduated, I started at Graftech in Cleveland, Ohio, Graftech International, and I worked there on a lot of proprietary R&D projects. But one of the projects that was actually funded by the Department of Energy in the United States was on lignin or biomass-based carbon fibers for, you could say, for functional, non-structural applications. In this case, we were looking at lignin-based carbon fibers as a raw material for making high-temperature insulation, which is used in furnaces, which is used widely in high-temperature furnaces. And so we had a very successful project there, which I'll talk more about later. And very recently, in about the last year, I just actually celebrated a few weeks ago my 1-year anniversary here at Oak Ridge National Laboratory, where I do work on nuclear graphite projects, in addition to some carbon fiber projects. In addition to that, one of the things that I'm very interested in, as you might tell by the talk title, is I'm very interested in the history of materials, and in this case, carbon and graphite materials, which I've tried to incorporate heavily into this talk. I'm a member of a number of professional societies, and I try to do a lot of STEM outreach, science fair judging, science fair mentoring, STEM mentoring, to try to encourage the next generation that will come in and take over the new challenges that we have. So a quick agenda for today. I'll talk a little bit about graphite, the graphite market, and what 125 years really means for the carbon and graphite industry. And then I'll highlight some different applications of carbon materials in very important applications that are very important today for the green economy, for electrification, and also highlight some challenges and opportunities, and where really there is a lot more work needed, despite the over 100 years of work and products that already have existed in the field of carbon and graphite. So to start a little bit at the beginning, I tried to design this talk to be very broadly of interest and applicable. So certainly many of you might be very familiar with carbon and graphite. In fact, maybe some experts and specialists already. But to start at the beginning, what is graphite? Well, carbon is an element, is a chemical element, as is well known. And from that chemical element, many carbon materials are possible. Too many for me to list here, but a simple way to look at a hierarchy would be that carbon can, you can think of sort of one-dimensional, two-dimensional, and three-dimensional bonding forms. If you look at a sort of a 2D sheet that's sp2 hybridized, you could say this could be a graphene sheet. And from this sheet of carbon, you can curl it, roll it, stack it, and get different carbon forms. But it's the particular stacking of this, sort of A-B stacking of these graphene sheets that we would call graphite. So graphite is a crystal structure of carbon, a subset of carbon materials. However, not just because there's this stacking that can occur doesn't mean that all graphite materials are this perfect stacking. And in fact, by mixing different forms and having less perfectly ordered sort of quasi-graphite materials, you can get a number of different structures, and also very important multi-scale bulk and surface forms, and leads to a variety of interesting properties, which is why carbon and graphite materials can be so versatile. Even thinking from a single sheet, there's differences between the edges and then the basal plane. The zigzag edges versus armchair edges have different properties. This leads to a wide variety of surface functionalities, surface characteristics, in addition to just the bulk. Normally, one would think about the world of graphite then as being either natural graphite based, which is natural graphite has been known for a long time. It's mined and processed. And actually, the quality and the purity of natural graphite can vary significantly depending on the mine, and even within a mine can vary depending on which vein, or it could be mixed forms of natural graphite within a particular mine. But the natural graphite does need to be processed a bit. So the natural graphite would be mined, and usually one wants to remove impurities or some different matter, some impurities, some elements from that, in order to get to a natural graphite flake, which then comes in different sizes, so that graphite flake is sized. And you could consider, how would you process that further? For example, for a lithium-ion battery powder process, those flakes would be spheroidized and further purified, and then maybe even coated before those natural graphite flakes could be used in a lithium-ion battery process. But of course, just on the flakes, there's many applications, and we'll talk a little bit about that as well. So one thing you'll see is not listed on here are the application of pencils, which I think for anyone working in the graphite space, the term do you work on pencils may often come up. And it may be also further thought that because graphite has been mined for such a long time, and maybe it's a very ordinary and very boring material, but it certainly is not. And there's a lot of interesting history in the field of graphite. So to take a quick diversion from this, natural graphite has been known for a long time, and in fact, in I think about the 1500s, it was found that natural graphite was an excellent mold facing material, or a mold lining material. And this was, as the stories go, this was found to be very good for casting of bomb shells, cannonballs, and of the like. And so graphite, and this in this particular source is talking about graphite from a mine in northwest England, from the Borrowdale mine, as it was called, not active today, but for hundreds of years was an important source of natural graphite for the British Empire. And they found that this actually was a strategic advantage. So natural graphite became a very important component of casting cannonballs for military applications, and so therefore became very prized and very expensive and heavily regulated. And so much so, as these applications were very important and the price was very high, these mines became very important to protect. And so in 1752, just to emphasize how important this particular mine in Borrowdale was, and how strategically important it was, it became a very serious offense for unlawful entry into this mine with the intention of stealing the graphite, with the potential penalties being prison, 1 year hard labor in prison, public whipping, or you could be shipped off to a work site in a faraway land, maybe never to return to your homeland. So it's a very serious offense to steal this graphite. And it was prized. This is a photo of some graphite that was mined from this particular mine in Borrowdale. This graphite was renowned for its high purity, and like I said, found very important military applications. So if you think that graphite has a boring history, it certainly does not. And many people probably trying to steal this graphite at these particular times in history probably just found how important it was, and could potentially face some very serious repercussions. Well, that's on the natural graphite side and a little bit of history. The other version of graphite, and probably the dominant one today, is synthetic graphite, where there is a precursor, a carbonaceous precursor that is heated to high temperature. An example of this could be a petroleum or a coal-based aromatic compound. Could have some other heteroatoms in it as well, but these aromatic compounds can be heated to high temperature, and if you get the right type of aromatic compounds, that will allow for this liquid crystalline or this mesophase formation before starting to completely polymerize. You will get good ordering of these stacks of aromatic compounds, and as you heat and heat, and as this cartoon suggests, you can essentially get to a very well-ordered graphite-like material. Usually not as ordered and as perfect as natural graphite, but can be very close, although the morphology is a bit different. But not every precursor will graphitize. And by controlling the precursor, the actual chemistry and molecular distribution in the precursor, you can get to a variety of almost graphite materials, or you can pick some materials that even at very high temperatures will not convert to this graphite structure. And today there's a big use for sort of a polygranular, composite of mixing together different ingredients and heat treating those. So, for example, a manufactured graphite material, as is schematically shown here, would involve mixing together these different carbonaceous particles that are sized with a pitch as a binder or a glue that holds it together, mixed and formed. There's various ways to form, like extrusion and molding. And these are heat treated all the way through graphitization temperatures, depending on what you're trying to get in the end, to create this composite, this sort of synthetic graphite composite-like material, which retains its very polygranular shape. But it's very hierarchical and very heterogeneous in its form, in that there are cracks and pores at different length scales that are very important for the final application and final properties. But even as you zoom in to very high magnification, you can see it's not just this sort of cartoonish, long range order of perfect planes extending in all directions, but there's grain boundaries, there's these hierarchical pores and cracks, there's a polygranular nature. So a really diverse set of structures that can be formed from a synthetic graphite, manufactured graphite process. So everything in between is very important for different applications. So where does that leave us then? We can make graphite, certainly can make natural graphite products, make synthetic graphite products. So today graphite really is considered a critical material for energy and electrification. And I'll highlight some of the applications and just some of the order of magnitude here. The term critical is very important because since natural graphite is not mined everywhere in the world, and the distribution of where graphite is mined has changed over time, and not everyone has access to the same building blocks, the petroleum and coal-based aromatic precursor compounds. It is considered a very critical material. Graphite demand is about 3 million tons annually, depending on how you carve out the carbon versus graphite part of this. However, the important point is that those about 3 million tons of graphite touch billions of tons of other material, like steel, like other materials in electric vehicles, for example. So you can roughly consider the market value is about 15 to 20 billion today, and you can get this number by looking at various market studies that are available to search. So somewhere in the 15 to 20 billion dollar range, and different applications are certainly growing the overall market growing roughly about 5% per year, with many different forms and applications. So in this particular schematic, I'm highlighting a couple what I think are very important to understand in terms of what graphite really does for technology and society. Starting with graphite electrodes, it's about a million metric tons per year, growing a little bit every year as more and more steel is made through the electric arc furnace process, which is where graphite electrodes are used. They are the electrical conduit to pass high power to melt scrap steel instead of using the traditional blast furnace route. This is about 25% of the total piece. Carbon fiber, although doesn't have necessarily the term of graphite in it, a lot of these fibers are taken to high temperatures that are in the graphitization range. So I'm considering them in the overall graphite market picture. About 100,000 metric tons produced every year, and about 25% of the overall market. A growing and very important application is graphite as an anode powder for lithium-ion batteries, specifically in this case, highlighting for electric vehicles, although lithium-ion batteries are used in consumer electronics as well. Some of these applications I'll touch a little bit more on. The use of flexible graphite in different applications like consumer electronics, for thermal management, for example, is very important. Not one that I'll talk about today, but is very important. And because graphite, a manufactured graphite article, is machinable, it's found a lot of applications in the electrification economy, specifically to use as insulation or different components for growing semiconductor crystals, which of course, as if you've tried to buy a car recently, you know how important semiconductors are for now automotive and every industry, there being a global bottleneck. But high purity, high density graphite, manufactured graphite materials are really indispensable for the semiconductor industry. Not something I'll talk too much about today, but you really can't go very far in energy, in electrification, without running into graphite materials really doing their job, sometimes behind the scene. And of course, for nuclear energy as well, very important. So graphite is irreplaceable in many applications. Demand is growing. And that's where we are today. But where did it all start? How did we get to this point? So to do that, we have to go back 125 years in time. And as I mentioned, that natural graphite has its uses tracing back to almost antiquity. And there were applications of, although they didn't call it graphite at the time, it was known by various other names. the term graphite didn't come into, I believe, the mid 1700s. Natural graphite was mined and found uses all the way back to antiquity, and in the industrial era, found use in refractories, as I mentioned, as sort of a mold facing or a lining during casting process to help create a smooth finish on a casting. Graphite for polishes, for coatings, and many people are aware of graphite as a lubricant, for example, but also polishes and coatings, and yes, pencils too. Pencils too are in there. But around in the industrial era, and in the United States, there was someone named Edward Goodrich Acheson, and many of you might be familiar with the Acheson name from the Acheson process or the Acheson furnace that is used for graphitization of materials. But Edward Goodrich Acheson was a real person, and he is widely credited with this first patent for the process of synthetic graphite manufacture by heat treating ingredients in an arc furnace, a small arc furnace to high temperature. Now, his intention wasn't necessarily to produce graphite. In fact, Acheson's first goal was to make diamond. He was trying to find a way to synthetically produce diamond. And the reason he was looking at diamond was, of course, for the need for abrasives. In the industrial era, you had to cut and grind different parts. And so diamond was the abrasive of choice. And so he thought, if I can create a process for making a efficient and scalable process for making artificial diamond, he would make a lot of money. Along the way, so unfortunately, he never did make synthetic diamond, and we would know why today because of the phase diagram of carbon. But he did make silicon carbide, and he is widely known then for his process for making silicon carbide, which again is heat treating these ingredients, clays and carbon at high temperature. However, while doing these runs of these furnace runs of silicon carbide, he also realized he was creating this other material in his furnace. And eventually, after much experimentation, he realized this was a high purity synthetic graphite that he was making in these furnace runs. And so he quickly moved to patent this process, which he patented in 1896. Now, although Acheson was the one to patent the application in 1896, he was not the first person to make, through high temperature heat treatment, synthetic graphite. Other folks had reported, even going back 20 or 30 years before him, had reported around the world accidentally making synthetic graphite, doing different experimentations with arc furnaces. However, their process was not reproducible, and those different researchers were not able to get patents, whereas Acheson was able to demonstrate his process was repeatable, and therefore was able to be granted a US patent. And so in the beginning, he was heat treating powders. He moved on to heat treating, sort of rods or cylinders or these monolithic pieces, and he found different arrangements of how to do that. And this is the kind of Acheson furnace that many people would be familiar with today, where you're using this furnace and stacking in a bunch of product and heat treating it to high temperature. So this process required a lot of electricity. And so when setting up a plant, he first set up a production plant in the Pennsylvania area outside of Pittsburgh. But quickly, as his business was growing, he needed a very inexpensive and large-scale source of electricity. So he set up a plant in Niagara Falls, which was he was taking advantage of some of the first electrification of the Niagara Falls and this vast hydroelectric power potential. And other people moved to put plants in the same area as well. But really, this was well timed. With being able to heat treat carbons to high temperature, to do it efficiently in these furnaces, really opened up a new industry. And there was a lot of rapid growth because these materials found very important use as electrodes for electrochemical and electrolytic processes, And also, this was just about the time that people were starting to really use electric arc furnaces to melt materials, like melt steel, for example. And so the timing was very good for electrodes for electric arc furnace steel making, which really took off in the early 1900s. And for example, there was a partnership between Atchison and Kastner, who was working with another folk named Kellner. So they have the Kastner-Kellner electrolysis process for sodium hydroxide. Sodium hydroxide is widely used in pulp and paper, in textiles, in soaps and detergents, for example. So there was a big demand for NaOH, and they found that these kind of graphitized electrodes were very good for this particular process. And of course, not long after this was World War I, and the demand for steel, the demand for materials, and then the post-war materials boom. So really, Atchison was well positioned from a timing perspective in order to take advantage of his invention, and he had other patents related as well. I was just highlighting two of them. If you're interested in the history of this, I would recommend checking out this book, Edward Goodrich Atchison, Inventor, Scientist, Industrialist, a biography, a well-researched biography about him, his ambitions, and his successes, his failures, and how he created not only this silicon carbide abrasives industry, but also the high temperature, the synthetic graphite industry, and then how that spread to a variety of applications. So moving on to a couple different applications then. One is, and as is very important these days, graphite for batteries. However, you may not know that carbon was always an important battery component, even before the days of lithium-ion batteries. And the perfect example of this is the Columbia dry cell battery, which came out, I believe, in 1896, was a very successful large-scale consumer battery, a dry cell battery, whereas there were other batteries that came before this, but this was really a commercial success in that it was manufactured at large scale and really was, again, well-timed with the electrification, the early electrification of the industrial economy. So this was the Columbia dry cell battery. It used, there was a central carbon rod as a current collector. It used a cathode and anode material. What was really important about this battery was not so much the chemistry, but some of the improvements. There was the zinc inner casing that sort of held everything together was the anode material. There was a cardboard outer casing, and because it was a dry cell, it did not matter the orientation that you used the battery. So it could be used horizontal, it could be used vertical. And this really was well timed for a lot of important needs at the time. So even as something as simple as the telephone, if you didn't have electricity coming into your home, which many people didn't at that time, you needed batteries to run a telephone. You needed batteries to run a flashlight. You needed batteries to start your car. If you had one of the early automobiles, you needed batteries for your alarm system for your home, and a number of other applications. So really, the success of this battery cemented carbon as a very important material for batteries. And this kind of chemistry is still available today to some degree, but remained very important, certainly through the 1950s, even as other battery technologies became available, like the alkaline battery. But today we recognize graphite as a very important part of the lithium-ion battery success story. This is recognized. This is certainly well recognized and well shown by the Nobel Prize in Chemistry in 2019, which is awarded to 3 gentlemen who really showed the progression of lithium-ion batteries from the cathode side and the anode side. And you can read about this. It's a very fascinating story, all the work that was done. But really, the culmination of this is that the final sort of safe and working combination of a lithium-ion battery that enabled the commercialization in 1991 by Sony used a petroleum coke anode and a cobalt oxide cathode. And this petroleum coke, we call it a sort of a hard carbon or a non-graphitized carbon, was the first total picture of lithium-ion battery to be able to be used safely. That is, they're very low risk of fire, very low risk of issues, whereas other anode materials, and certainly even using lithium as an anode material, although technically worked, was not going to be a safe and scalable technology. And so the Nobel Prize recognizes all the developments that were done here. Now, strictly speaking, this very first version wasn't using graphite in the exact sense that we use it today as a true intercalation material, because this was a hard carbon and it used a slightly different electrolyte formulation than what's used today. But this did go a long way in really demonstrating and proving that this could be workable and that this had a future. And of course, from there, lithium-ion batteries have permeated very, very widely. So it leads to the question, why graphite? Why, despite graphite not being the sort of the best anode material, why is it the main anode material today? And really, I think number one, it's because there's acceptable safety and stability, because you're working with lithium and different chemistries, and some of them being potentially flammable or explosive and a bit dangerous. Really, for the battery to work, there has to be the acceptable safety and stability, which graphite was eventually shown able to be worked into that. And of course, graphite is relatively low cost and it's available material. So graphite became the sort of a dominant anode material for lithium-ion batteries. So what's going on? Well, for an intercalation lithium-ion battery to work, lithium ions have to get in and out of this graphite structure. And so one idealized way to look at it is with this picture. Whereas if you have a particle that has these perfectly oriented planes of graphite, lithium ions can only enter in through these edge areas unless there's defects in the basal plane. The only entryways into the graphite are through the edges. And so to get the full potential of graphite, then all of the available sites through these staging mechanisms have to occur. And there's still a bit of work to do and maybe some clarification that's needed on exactly the mechanism of lithium ion insertion into the graphite lattice as an intercalation compound. But nonetheless, you get to the point where at the full part, it's fully lithiated, and this is assuming the graphite is only letting in lithium ions at the edges. But this is a very idealized picture. This is not reality. In reality, graphite particles that are made like this have a macro structure. There's shape and size. There's porosity. And if you think about these graphite potatoes that are made through pounding and shaping of a graphite flake, there is internal porosity. That is in there. And this is in this paper, they certainly visualize these pore networks using X-ray tomography. So you don't just have this perfect picture here. You have a macro structure, a microstructure, and a macrostructure. But importantly, to make all of this work, you need a stable surface film or interface, essentially, where if you did not have the graphite covered with this solid, as they call it, solid electrolyte interface, there would be continuing degradation through the intercalation and deintercalation of the graphite structure. So it's this barrier that's formed of different salt compounds that really enables the lithium, the graphite to be used in today's lithium-ion batteries. And so the full picture at the nanoscale, the surface scale, the micro and macro scale all have to come together in order to make graphite the success that is today. And many developments occurred over a period of decades to make this happen. And as you can imagine, defects that occur in the plane, the actual crystallite sizes and shapes within a particular graphite. So all of these are very important and are still why graphite is not fully worked out today. So although this is the dominant material, it's still not perfect, and there's still energy storage gaps. So the trend today for electric vehicle manufacturers is to blend in silicon to improve the capacity. This is because silicon has a much larger reversible capacity than just pure carbon from a battery, just a battery energy storage perspective. But on the other hand, you have with the lithiated silicon a much larger volume expansion, which means the tendency to crack and to spall. And so balancing that is a bit of a challenge. Fast charging is still a gap. Everyone, it's widely recognized that fast charging is one of the key barriers to adoption of electric vehicles. And so because of the way that these ions get into the graphite structure, it's not equally accessed from all of the surface area. So in order to improve the ability to get these ions into the structure, you really have to tailor the graphite at a nano level. Otherwise, you will just end up plating lithium onto the surface, and that just will kill the battery. So all of these really have to be solved in order to move forward. And even though there is acceptable safety and stability today, for broader market application and for continuing growth of electric vehicles, these issues remain to be solved. I do want to point you to this paper, Selecting the Best Graphite for Long Life High Energy Lithium Ion Batteries, which was published in 2018. If you were very interested in some of the more technical details and a comparison of different graphites in a test cell, this gives you some more detail into how different some of the graphites that are commercially available today for lithium-ion batteries, exactly how they stack up versus each other, and why different morphologies and different surface chemistries lead to different performance in lithium-ion batteries. And so where we are today, we have a market of about 200,000 metric tons of natural and synthetic graphite that are used today for lithium-ion batteries, both between electric vehicles and for consumer electronics. And although it's called a lithium-ion battery, graphite is a big component by weight. And this is some data taken from the Volkswagen Group components. You can see in their sort of example 400 kilogram battery, 71 of that is graphite, much more than there is lithium in the material. And second really only to aluminum, which is used more for some structural components and some other components, and the actual nickel that's used in the battery as well. So very important material by weight, and you could see why, as you have a battery, a electric vehicle battery, why really we talk so much about graphite. This could be either in the synthetic or natural graphite form, although the split of this and the distribution of this will change over time. So although 200,000 metric tons is about what is used today, if you want to see the electric vehicles grow and become dominant in the world, I mean, this number, this amount of graphite will have to go up by perhaps a factor of 5 or 10 or more. So this would completely, obviously, change the supply demand for graphite, and you see many people working in this space because of that. So the role of graphite is not being diminished anytime soon. Yes, there will be other anode chemistries. Yes, there will be changes that occur, but for the next several decades, really graphite is going to be the key material for lithium-ion batteries. There is a lot to be said on other applications too, and in fact, even for nuclear power generation. Graphite has been around from the beginning here as well. Graphite was used in the first critical nuclear reaction in 1942. Because graphite does have a high scattering cross-section, low absorption cross-section, high temperature stability, and the ability with the porosity to accommodate irradiation. So you do have where graphite has been around from the beginning of the nuclear age and continues to be. Different designs adopted by different countries and different time periods, have kept in some designs graphite as a moderator and reflector material for both gas-cooled and for molten salt reactor designs. One very important part of this is that graphite can often be considered the life-limiting component of the design, in such that the degradation of the graphite by irradiation or by other mechanisms could be the reason why the design has to be either the graphite has to be refreshed or there has to be a shutdown. And so there's different forms of graphite bricks and blocks that have been used in different designs, kind of highlighted here, and used in various arrays in the overall reactor design. But I think the important thing to stress, as many of you probably know, is that there is really no standard graphite grade. There's no standard manufactured graphite grade. Each manufacturer makes a slightly different material, depending on the raw materials, depending on their process. And so that's one issue already, is just the diversity of different graphite microstructures that can be formed from these different microstructures that represent the different grades. And then, of course, the changes over time. Graphite properties change with irradiation. They change with potential environmental degradation like oxidation. And so there is an ongoing and very urgent need to better quantify this. There has been many decades now, 60 plus years of work on the study of graphite for nuclear applications, but still not a complete picture, because some of the graphite grades that were studied earlier on are no longer available. So new graphite grades are available. They're not fully characterized. And so there really is ongoing and urgent work to really understand all these mechanisms and how they could affect the integrity of a reactor. So irradiation is one important one, as high energy neutrons from a nuclear reaction hit a graphite lattice, can knock out carbon atoms into an interstitial position. If you do this enough and you form enough vacancies and enough interstitials, you can get expansion of one direction and contraction in another direction of the graphite lattice. And this is at the crystallite scale, the very small scale. Of course, there's effects occurring at the kind of microstructure scale as well. So all these changes to the graphite structure result in changes to the volume, changes to the tensile strength, changes to the thermal expansion coefficient, which are very irradiation dose and temperature dependent. And so depending on the design envelope of the reactor particulars, all of these need to be incorporated into the integrity understanding, just from the effect of the irradiation side. And of course, there is potential for other degradation as well. The irradiation degradation will happen over time. There could be, in an accident scenario, perhaps air or steam oxidation of a graphite component. Because of the open pore structure of graphite, the oxidant can get inside of the graphite pores and attack not only the surface, but through the open porosity, attack the walls of the pores at some depth, sometimes several millimeters or more inside the graphite. So there's an overall attack and oxidation or gasification of the graphite, which is temperature dependent and microstructure dependent. But also there's simultaneous irradiation occurring, which is only really beginning to be studied more in depth. So we need to understand not only the overall loss of carbon and graphite from the structure, but how the pores grow at some depth inside the material, because as this plot suggests, there is an exponential decrease in the strength of the graphite article with weight loss. Roughly speaking, about 10% oxidation would cut the strength in half. And so even a few percent oxidation can really start to change the integrity of that graphite material. And so recently, some work that I've been involved in has been looking at how we can better understand the pore structure effects. So different, as was suggested on the last slide, different pore structures are formed by different grain sizes and forming conditions. And so we need to understand really how that is going to lead to these strength loss. And it's not just about strength, it's about the Young's modulus, it's about the thermal expansion coefficient, like we showed on the last slide, thermal conductivity. Many properties are going to change with the radiation and oxidation, and those need to be really better understood. There's not standards for studying all of these, and so there really is an urgent need there. So still in the energy space, so we've talked about batteries, we've talked about nuclear power generation. Carbon fibers are a well-known application for graphite materials, and really it's usually been about carbon fibers for composites. And from the early days, there were carbon filaments. You could say maybe the first important use of carbon threads or carbon filaments was for light bulbs. This was a bright idea, but still not a structural type of application. So really the 1960s, maybe the late 50s and early 60s was really where we got into the era of high performance carbon fibers, rayon, pitch, pan, and eventually pan became dominant as the carbon fiber precursor for aerospace applications, for some, well, certainly for the aerospace applications and some other applications as well. Carbon fibers really became critical for their strength, stiffness, and depending on the type of carbon fiber, the electrical and thermal conductivity. So carbon fibers made from pan versus carbon fibers made from pitch have different processes. The pitch-based carbon fibers, because of the long-range structure, graphitic structure that can develop, can give a good thermal and electrical conductive fiber and composite. But they also have different properties from a stress-strain perspective. And so this chart quickly illustrates where the different carbon fiber precursors tend to fall. So they're all quote unquote carbon fibers, but they're very different depending on the precursor. The amount of strain that you can get to failure is very different. The high modulus or pitch-based carbon fibers tend to give a very low strain. There's high modulus and standard modulus pan-based fibers, which can give different strain to failures. And this is contrasted versus glass fibers. Glass fibers are widely used in some applications as well. They have a much lower modulus that's available with carbon fibers, but they can give an acceptable strength, which makes them, and they have a lower cost, which can make them very competitive. So really, what kind of fiber you need depends on what kind of application you have and what your allowable cost is. But from a structural perspective, there's a wide space available where different types of carbon fiber precursors can fall. But it's not just about strength for carbon fibers. There's other applications as well. And in fact, as you get away from the aerospace area, there's lots of growth potential for carbon fibers and composites if both the cost of the fiber can decrease and part manufacturability can increase. You can consider high volume automotive, high volume civil or infrastructure repair, for example, bridges or perhaps reinforcing bridges for seismic activity. There's the energy generation from wind turbines. Mostly glass fibers are used in this space, but there's potential to further the application of carbon fibers in the space. And we can't forget about functional composites. I mentioned earlier on some insulation applications. There's filtration applications. So there's a lot of research into the alternative precursors and processes, especially if you're targeting something that doesn't need the high strength, or in some cases doesn't need the high stiffness. A perfect example of that is some work I was involved with lignin or biomass as a carbon fiber precursor. If you're familiar with lignin or some other biomass sources, they have a lot of carbon in them, which is great. It seems to be great as a carbon fiber precursor. But you realize that in addition to all the carbon, they have a lot of other they have a lot of functionalities. They have a very branched amorphous structure to them. So they're not going to fall into the traditional carbon fiber precursor category. But what can we do with them? Can we do anything with them? In this work that we did, we showed that you can take different biomass sources. In this case, we looked at some softwoods, some hardwoods, and some true kind of waste biomass, and by using different extraction and cleaning methods, we could get to a raw lignin that could be melt spun into fiber. And we looked at some different treatments. We looked at some plasticizers. We looked at some stabilization accelerants to help shorten the stabilization time. But we could get to some acceptable carbon fibers that could be milled and still retain their shape and integrity, for example, for use in an insulation application. This work stopped at the level of starting to scale up, but with the work that was done, we showed that different lignin sources did have potential with a fairly decent carbon yield of about 40 to 45%, and low enough ash content that would make them suitable for these very critical insulation technologies. So this was some of the first work to really try to link together the fundamental lab side with an actual application. I'll say a few words on graphite electrodes for a very high volume application, which is steel recycling. And as I mentioned in the slide on Atchison, this was actually one of the very important applications early on. So this is a long-running application of a graphite material, of a synthetic manufactured graphite material that has grown over time. Today, worldwide steel production is almost 2 billion tons each year. And 30% of that, on a global average basis, 30% of that is produced through the electric arc furnace process, which is essentially where you're recycling scrap steel in a very large furnace, where the graphite electrode comes into play as the consumable conduit between the power supply and the basket or the bucket where all the scrap steel is. And in order to accommodate different furnace sizes and different applications, graphite electrodes come from anywhere from a diameter of 75 millimeters to 750 millimeters. And these graphite electrodes, like as I mentioned, are really the very critical conduit of passing the electricity down into the steel. So why is graphite used here, and why hasn't there been another material that's come in and replaced this? Well, graphite is uniquely positioned for its low thermal expansion, high electrical and thermal conductivity. And despite attempts to replace this or use other materials, there really is no known commercial replacement besides graphite electrodes, these cylinders that are used for EAF steel making. And as one electrode is consumed, another electrode can be placed on top of it, and you can continue making steel. So in this, again, although a very long-running application, it's a very aggressive, it's a very extreme multi-physics environment. The raw materials and processing for this are very stringent. It takes a lot of knowledge. There's a lot of proprietary knowledge involved. The market is highly consolidated, very competitive globally, and really very little published on this. But a very critical part of this, and as I said, graphite in this process is touching over 30% of the world's steel every year, and growing. Eventually, this will continue to grow and will be a much larger percent. So we've talked a lot about different applications for synthetic carbon and graphite, a little bit about natural graphite materials. One important topic these days, of course, is what is the environmental effect of what the process is doing. And admittedly, synthetic graphite is an energy-intensive material. To graphitize a precursor, that is to take a carbonaceous precursor all the way to 2,800, 3,000 degrees Celsius, requires a lot of electrical energy. And depending on what units you want to work with, in around the, let's say, 3 to 6 kilowatt hours per kilogram of carbon or of, in this case, graphite produced. That compares to be just about the same order of magnitude as energy required for the blast furnace, basic oxygen furnace, crude steel making. Although the energy sources are different. For graphitization, it's primarily electrical energy. This is much less than the electricity needed for primary aluminum smelting, which is very, very energy intensive, but much more so than what electricity is needed for, example, melting steel. So synthetic graphite is an energy intensive material in its own right because of the graphitization process. But through making synthetic graphite materials, many other technologies are enabled, which are playing an important role in trying to get to a cleaner and greener world. For example, graphite, as we discussed, is the critical material for enabling electric vehicles through lithium-ion batteries. And electric vehicles directly emit zero CO2. However, charging the battery requires electricity, and depending on where you're charging it at in your location, the source of that electricity could be emitting CO2 that varies very widely. Even in the United States, state by state, there's very different distributions of where electricity is generated from, coal versus wind versus hydroelectric. And so that electricity is not equivalent in its greenness. So the graphite's important to enable these electric vehicles, but still there's work to be done on generating cleaner electricity. Carbon fibers, for example, could play a very important role in light weighting of vehicles. There's a rough estimate that a light weighting of a vehicle by about 10% can increase fuel economy by 6 to 7%. This is, of course, assuming a internal combustion engine. But as we move to electric vehicles more and more, perhaps carbon fibers will play a role there. And there's what's called the mass compounding effect, where as you lighten the vehicle, you can reduce the dimensions of other features on the vehicle as well. So light weighting can beget more light weighting. Nuclear reactors could play a very important role in a green economy. The reactors themselves do not emit any CO2 directly. However, mining and refining reactor fuel is certainly very energy intensive, and it has to be considered in the overall picture. And of course, disposal of the graphite and the nuclear waste are still unresolved issues in many senses. And then from the world needs a lot of steel. EAF steel produced through the electric arc furnace process emits 1/3 of the CO2 than the traditional blast furnace, basic oxygen furnace route. And so as more and more steel will be made through the EAF process, although it means more synthetic graphite, this does have a big impact overall of favorably impacting CO2 emissions. And as we know, activated carbons are excellent adsorbents, some of which are being explored for their ability to capture carbon directly from the atmosphere. So despite everything, carbon materials really are at the forefront of both energy, technology, and electrification. They have been. Different applications have come, some have gone. Some applications like steel have remained the same, but there will be more applications coming in the future that I'm sure we will hear about in the years to come. But I'd like to conclude really with some challenges and opportunities. So as I've tried to take you through a 125 years of synthetic graphite journey, one of the truths currently is that many graphite materials do start with coal and petroleum hydrocarbon aromatic residues. These can be very complex mixtures that come from the refining and processing of coal and petroleum materials. And we want these aromatic compounds in particular. Each source could be different. Each barrel of oil, each coal mine and the coal from it can lead to slightly different aromatic compounds in terms of not only the distribution of aromatic versus aliphatic content, but the length of the side chain, heteroatoms like sulfur and nitrogen. So there are very complex mixtures that go into the making of many carbon and graphite products today. And understanding this complexity remains a important barrier in order to unlock new sources of carbon and graphite precursors. Even the polymerization and pyrolysis of pure aromatics can lead to a diversity in structure. So that means it's good in the sense that carbon and graphite materials can be tailored, but also challenging in the sense that we need to understand the multi-scale and hierarchical nature of the materials that come from these precursors, and how to unlock new precursors that maybe can be coming from a more renewable source. So how do we study this? As I said, there's a lot that's not well known. There's some very interesting developments that I personally am excited about. I'm not directly involved with, but personally very excited to hear about. I've recently read about the use of high resolution atomic force microscopy using a carbon monoxide functional tip to really directly image aromatic hydrocarbons. And by doing this, although there are many challenges with this technique that haven't been fully worked out, able to almost visually see reactions, the before and after of certain reactions, and really understand what are the nature, the distribution of different products from, let's say, a reaction of a hydrocarbon or the polymerization of a hydrocarbon, understanding the role of the side chains, the length of the side chain, the distribution of different compounds. This work is still, in its early, its first decade or so, but still, I think a very interesting potential again to directly image these hydrocarbon bonds and be able to follow reactions. Also, how do we model and understand the complex structure and evolution? There's a lot of papers now and some very interesting work on using reactive force field methods to study the precursors, to study the evolution. So, for example, I'm highlighting some work that I recently found from Jonathan Matthews at Penn State, looking at devolatilized coal char and the complex aromatic structures that are in there, and other people certainly actively working in this area. And so, what about machine learning? How will machine learning help us to better understand the complexities and the structures and evolution? Each application of carbon and graphite really does require a deep understanding because of the diversity of how materials are used, from steel making to batteries to carbon fibers, to many other things as well. Each application is unique and requires a unique understanding of structure property relationships, some of which are more well known than others, but we need more advanced tools and a more systematic understanding. In the end, though, this means a lot of great challenges for scientists like me, scientists like us, and great opportunities for the next generation. So with that, I'd like to thank you for your time today, and happy to have a discussion and take any questions. So thanks very much, everyone.
Okay, thanks so much, Ryan. That was absolutely fantastic. I just wanted to have a little quick spruik for our next carbon webinar, which will be the first time that we've run an online poster session. So the format is a landscape poster, and there's a template that's shown on the screen, and it can be downloaded at the sign-in form if you want to use it. You don't have to use it, but it's just there if you want. And if you've got something else, as long as it works for a computer screen, that's fine. And so the idea is that we'll have an online Zoom session where especially students and junior postdocs can present their posters and allow for conversations and questions to be asked. So it's a great opportunity for students and early to mid-career researchers. And we're going to have a competition for the best student and the best early career researcher who will be given a chance to present a short award talk in a future carbon webinar. So at this stage, we need anyone who's interested to sign up to the website. Jake is about to add a link to the Zoom chat so you can sign in to the webpage. And please do what you can to promote the event through your groups to prepare a poster, as it's only a fortnight and a bit away. So we'll be sending around an email to further promote this, and I think it's a great thing that we can do for our students and junior researchers. But look, that was an absolutely fantastic presentation, a real tour de force. It's amazing to see how many areas where graphite is a critical mineral. I'm used to hearing the rare earths described as a critical mineral, but not so much graphite. I think it was absolutely brilliant. So on that note, I'll just like to thank you again for presenting such a fantastic Graffin lecture to all of us, and I'm sure you'll look forward to presenting it again across North America, especially as you get to travel. Okay, so with that, I'll bring the webinar to a close. Thanks to all of you for signing in. Please do go over to GatherTown, and I normally use Chrome if that matters for your choice of browser. And it's a great way to have a chat to finish off the morning or the afternoon or evening, wherever you are. So good night from Perth.
Thank you.